Okay, so last time what we were doing is we discussed this thing, and this is basically the gradient descent algorithm. And what we were doing is we were using single feature here, and using this single feature, we got these parameters of the model which we adjusted as per the optimization strategy which we were using, and the optimization strategy that we were using was gradient descent. And we also saw that how these lines are changing as per the iteration when it moves from this side to this side to this side to this side. So we already discussed in details in the last lecture what was happening here. So can you tell me what is the drawback of these equations? Let us say if I use these equations as such, will there be any drawbacks here, like of implementing it numerically? Will there be any drawbacks? Anyone?
So it will take time.
Why it will take time?
If the data set is large, so
Yeah, so
maybe the possibility that calculating such an expression will take time.
yes, so actually, as the training sample increases, you can, obviously you can realize yourself that if the training sample increases, it will take large time to do the summation sides, okay? Because you have to sum them up by multiplying the corresponding, model estimate subtracted by the actual label times the feature. So as you increase the size of the training samples from m, which is typically in millions, so as you keep on increasing the size, the computational complexity of this particular equation will increase, and it's difficult to uh, basically it will slow down the gradient descent algorithm. That is the main thing here. So what we do is we try to overcome this problem of summation which is here by using by employing matrix multiplications, because most of the softwares that you are using, like MATLAB, I don't know whether you have used it earlier or not, but MATLAB, fundamentals of the MATLAB are based on the matrix multiplication. So it basically performs faster computation if you provide things in the form of matrices. So what we will try to do is we will try to see whether we can eradicate, whether we can remove this summation, and can we really implement this particular expression here in the form of matrix multiplication or not. So here if you see the technique of converting these summations, the ones which are written over here, the technique of converting these summations into a matrix format is basically also called as vectorization. So we try to vectorize the codes, we try to make the codes faster by making vectors implementation of these matrices, of these values. So we try to make vectorizations of these expressions. Basically what it means is we try to convert these expressions into matrix format so that we can implement them faster. So if you see here, let us say you have a and b, and a and b are basically one dimensional vectors. So if your a is let us say 1 2 3, and if your b is let us say 4 5 6, then you know that if you try to write the for loop for multiplying a and b together to get you to the answer z, then you know what is the process of doing it. You will use a temporary variable, and then you will use for loop which will run from 1 to till the elements of this vector. Let us say it's n, right now it's 3. So you will run the for loop for I running from 1 to 3, and then you will add the corresponding indexes of these matrices of these one dimensional vectors and store in the temporary variable, and finally you will get whatever results that finally the temporary variable will get the multiplication of these two vectors. So as you can see here, as you will increase the sample size from 3 to let us say 1000 or millions, the time it will take for the for loop to execute this will also increase. And right now this is for one dimension. If the dimension of this particular matrix increases, then obviously it will also create more troubles for execution, because it will take more time, because then you will have one more for loop going inside. So if it's a three-dimensional matrix, then again it will have another for loop. So there will be a cascading of the for loops as the dimension of the matrix increases. So you can see that as the for loop cascades like one after the other, if you are using for loops, then it will slow down the computational process. But on the other way around, if you do A transpose B, then you can clearly see that within one step you will get the answer for this summation. So if you do A transpose B, it's very, so you are from a mathematics background, I hope you will have no doubts in calculating this. You know what this is. So A transpose B is nothing but you transpose the vector A and times the B. So you will get within one step what is the Z value, which actually when you are using simple for loops, you know how much time it will take, and here it will be computationally fast. And the reason for this matrix multiplications are computationally fast because the MATLAB and the Python softwares which are MATLAB and the Python softwares which are you are using, they have a very highly sophisticated optimized libraries. They have a very highly sophisticated optimized libraries which can do matrix multiplication very fast. So they have very good employees which are actually efficient in implementing all these matrix multiplications in a more efficient way, and that one in a more efficient way, what I'm trying to say is their programming skills are very to the top level, and they can implement these matrix implementations in a very faster way, rather than if you are doing the same thing, the time taken by you will be more as compared to the way they have coded. So these libraries which are there in the Python and the MATLABs, they are highly optimized and are very fast. So that's why people try to convert these expressions which involve for loop into a matrix multiplication, so that they can speed up their executions. So the main objective of doing vectorization is to speed up the execution. You can also check in your laboratory experiments also, like if you want to do it through matrix or if you want to do it through for loops, you will realize that how fast it is if you do it through matrix multiplications. So within seconds you will get the answer, but if you are using for loops, you will get after few seconds. So that is the main objective of doing vectorization here. So if I want to vectorize the codes that we are having here, so the next objective is how to do vectorization of this code. That is our main objective. So let us go step by step and see how we can vectorize these two equations and see how matrix versions of this can be implemented. So our objective is how to convert these equations into its corresponding matrix format. So if you see here, we already know the model that we are having, which is theta 0 plus theta 1 x1i. This is the model which we are constantly talking about, and here you can see we are only using a single feature, so that's why we are writing 1 here. I hope you know that. So now the process of converting this equation into matrix format we will start. So what we will say is, let us say theta is actually nothing but it's a 2 cross 1 one-dimensional vector. So I am writing it like this. And as you know, we will define a vector also, which is x of I, but this vector right now has only single element. So right now, because we have only single feature, so that's why we have a single element. So this single element is in this vector xi. Later we will see when the features increases, then this x1i, which is right now a single element, will be replaced by a vector which is which will be like this xi1, xi2. We will see that. So right now, because it's a single feature, so it's represented by a single element here of this vector. Now what we will do is we will define a bold x, which is written over here. You can see I have written it in a bold format. So this is nothing but it's a transpose of the vector that you are defining over here. So right now, so what we will do is we will actually cascade these transpose of the vectors which is defined over here for all the samples. So right now we have m samples here. If you recall from our earlier convention that we were using for this problem statement, we had m training samples. So we will actually cascade, on top of each other. We will, put them in rows like this. So this is the first row, this is the second row, this is the third row, this is the third row, and then this is the mth row. And you know that each of these vectors itself have only a single element. So if you do a transpose of this element also, it will remain the same. So this is the one dimensional design matrix, which will be which we are calling as bold X, and you can see the dimensions of this matrix. It will be m cross 1. So it's a design matrix. We call this as a design matrix. So any questions here related to this? Okay, so this is the design matrix. Now what we do is we actually again write another convention where we use x dot. So this x dot is nothing but it's a simple bold X, and 1 is appended to this vector or matrix, or you can say this one dimensional vector. Yeah. So once you append a 1 into this, what you get is this expression here. So this expression, what we are saying is this is basically nothing but x dot, and the dimensions of that is m cross 2. So basically, if I want to extract the second row of this x dot matrix, then what I will do is I will write like this. So it is x dot, in the brackets it will be 2. So basically what I am trying to say is we are trying to find out the second second sample of this matrix. The second sample of this matrix is nothing but the second row of this matrix x dot. So this x dot is nothing but this thing. Okay, and now here if you see this one, the the second if I want to extract the specific element of this matrix, then I can do x dot 2, and if I want to extract the second element of the second sample, then it will be nothing but the feature itself. So it will be x dot 2, x to the power 2, and then subscript 1. So basically when you write like this, it means you are actually accessing the feature only. But if you are writing like this, it means you are actually getting the row of that particular x dot. Similarly, what we do is we actually label the y's also in the same way. So what we do is we actually write labels like this. We are using first label for the sample 1, second label sample, then we have mth label sample, and the dimension of this is also called m cross 1. So this is the dimension of the matrix. Any questions here? Anyone? Are you able to follow what's going on in these slides?
Yes, sir.
Okay, so once we have these matrix implementation, or you can say matrix representations of these formats, once we have that, what we will do is we will actually convert this into a matrix format now. So if I want to convert this into a matrix format, what we can do is I will rewrite this loss function again here. So you can see the loss function is again written, and I have written this again in the format which we already know. And then what we will do now is we will try to vectorize this expression. By saying vectorize this expression means we are trying to convert this expression into a matrix format. And why we are doing it? We are doing it so that we can calculate the loss function in a very efficient and fast way. So now this particular expression, if you look closely, this is nothing but it's a matrix multiplication of this and this, which we have already defined which we have already defined here. So we are actually trying to vectorize the internal of this loss function first. So if I vectorize this first, then it will become this. And you can see here basically what I am trying to do here is we are trying to find out the ith sample of x dot, and then you have theta here. So if you multiply these two, you will actually get this as such, and then we have this yi. So note here, this yi is not converted into the matrix format right now, but right now we are keeping it as such. and here this part is converted into the matrix format. And this step is basically a single step, so we are calling it a single vectorization step. We are not completely doing the vectorization, we are partially doing the vectorization, so that's why it's a single step of vectorization. And here this is the thing, and now we will try to convert this into this complete expression into the matrix format, and this can be done by by using this expression. So once you write this expression, this is actually equivalent to this expression which is given over here. And you can see now the internals of this is now x dot, and it's not I here. And if I is not there, then the dimension of this matrix will become m cross 2. Whereas the dimension of the theta will still remain the same because you have two features, and because of that two features you have 2 cross 1 here. If the features, you have only one feature, so that's why you have 2 cross 1 here, and the 2 is coming because you are appending 1 here. That's why 2 is coming, otherwise it's a single feature, so theta 0 and theta 1. So this is 2 cross 1. So we have this as our matrix, right? Theta 0 and theta 1. So this 2 is coming because of that. And here the dimensions of x dot is m cross 2, and you can see m is basically taking care of this summation which is over outside. Right now here in this x dot I, you only had 1. So we were doing sample by sample as I is varying from 1 to m. But now if I remove this summation, in order to remove this summation, what we do is we change this x dot to m cross 2. And I hope you know this, because this is an x square can be written as x transpose x. So we are using this particular expression to write this particular square expression into this thing. So here if you observe, the dimension of this matrix is 1 cross m. If you completely check this, it will be 1 cross m, and for this it is m cross 1. So once you multiply these two dimensions, you will get 1 cross 1. So loss function will be a single value, and it will not be a vector. It will not be a matrix. So that's why the dimension agrees when you do this multiplication. So whenever you try to do a vectorization of any expression, you have to cross check it with the dimensions whether it's agreeing or not, because if these dimensions are not agreeing, obviously your code also will throw an error. So you have to check. If your code is throwing an error, that means somewhere your matrix dimensions are not agreeing properly. So you have to check that properly. So I hope you can check yourself that the dimension of this matrix and the dimension of this matrix complete will be 1 cross m and m cross 1. Any questions here? Okay. So this is the loss function that we have for this particular loss function which we have over here. So what we did is we converted into a format which is a matrix format given by this side. So now again what we will do is we will try to expand it further, and we will cross multiply inside all these terms and see what we can gain insight from when we multiply all these terms with each other. So once we start multiplying all these terms inside, that if you do a minus b whole transpose is nothing but it will be a transpose minus b transpose, and then you have this expression, and then you can actually further expand it by further dividing this transpose into individual transposes, and then you have this expression which is given over here, as simple as that. And then once you cross multiply all these terms, you will get 4 terms which are this one, this one, this one, and this one. So these are the terms which you can yourself can check whether these terms are actually the same or not. So 2 observations which we can see over here is that this is basically a transpose of this. So if you take a transpose of this, you will get this. And the second thing that you will see is if you check the dimensions of these matrices which are over here, then the complete dimension will be 1 cross 1, and here also it will be 1 cross 1. So it's a single value on both the sides. Like this one also is a single value, this is also a single value and a scalar. So if it's a scalar value, then obviously you can take any one of them, and I have taken this one as one of them, and since we are having these two as the same values, so we will put it as like this. So I am taking this one, so that's why 2 is coming over here. So now we have this expression which is given over here. Then now what we will do is we will try to calculate the derivative of the loss with respect to theta, because that is the main thing, because it will be used in our gradient descent. So that's why we will calculate the derivative of the loss with respect to theta here. So if I do the derivative of the loss with respect to theta, what you will get is this. If you take the derivative of these matrices, then you will get to know this. So if you don't know how to do derivative of the matrices with respect to the vectors, and the derivative of the matrices with respect to matrices, so please check internet. I will not go into the details because it's a very fundamental thing, and I expect you guys to know this because you are from a mathematics background. So this is actually, you must know it. So if you do not know how to do the calculus on the matrices, try to check it on your own and see whether you are getting these same results or not. So what we are doing is we are taking the derivative of the loss with respect to theta, and the derivative of the loss with respect to theta will be, for this part it will be this, for this part it will be this, and there is no theta involved here, so it will be 0. And from here what you can do is you can actually calculate theta transpose is as this one. This is the expression for theta transpose in the matrix format. So this is the matrix format, and here all these elements are matrices, and you can see it's very easy now to calculate theta star, right? So what you have to do is you have to actually first of all create a x dot matrix, and then you pre-multiply this x dot matrix with x dot transpose, and you take the inverse of that followed by x dot t times y. So you know that this is very simple matrix multiplications in which inverse is also involved. So once you do these type of matrix multiplications, straight away you will get the value of theta star. Straight away you will get the value of theta star, and there is no need of doing iterations which we were doing in case of gradient descent. So it's a very fast way of doing it. So can you tell me what is the dimension of this matrix which is given over here? The one which we are doing the derivative of the loss with respect to theta. Can anyone tell? What would be the dimension of this matrix? Yes. Roll number 14. Can you tell me this? Roll number 14.
Yes, sir.
Can you tell me this? What would be the dimension of the loss with respect to theta? Do you know?
No,
What is your background? Your mathematics background or what?
no, sir, not mathematics.
So from which background you are?
Sir, commerce.
Roll number 17. Your voice is not audible. Roll number 17. I cannot hear you.
Sir,
Yeah, please.
sir, hello.
Yes. What will be the dimension of the matrix partial L by partial theta when I have calculated it?
Sorry, sir, I don't know.
Roll number 25.
Yes, sir.
Can you tell me what will be the answer?
Maybe 1 into 1, 1 cross 1.
No, it's not 1 cross 1. 32. Yes. Can you tell me the answer?
Sorry,
42.
Yes, sir.
What will be the answer? You people are very weak actually, I guess, compared to your seniors. I don't know. But if you have any doubts, why you are not asking me? That's the main, you know. Okay. Okay, the derivative of the loss with respect to theta is nothing but it will be a dimension of 2 cross 1. It will be 2 cross 1 because it's a scalar and you are dividing this scalar by a one dimensional vector which is theta. So if you go through the vector calculus, you will get to know that it's a 2 cross 1 vector, and that's why your theta hat which you are estimating here is nothing but it's a theta 0 theta 1. That's why you will get these two, because you have single feature with theta 0 which is the bias term. So this theta hat is nothing but a 2 dimensional 2 cross 1. So anyone can anyone tell me why will there be any as we can see there is no iteration involved, so you can easily calculate theta hat, but will there be any error here? Not error, is there any disadvantage here? Can anyone tell, like what kind of disadvantage this method is having? Anyone? Okay, so the disadvantage of this method which is over here is basically the inverse of the matrix that you are calculating. So the inverse of the matrices that you calculate actually takes a lot of time. So if you do it numerically onto the software also, it will take time if your dimensions of this matrix increases. And you see the dimension of this matrix, if you see, it's nothing but it's a right now for this particular case it is 2 cross 2, but as the features increases, if you use large number of features, and we are using n number of features, so in that case this dimension will become n cross n. And you can see normally we use a lot of features, like 100 or 200 or 300 or maybe 1000 features we use for practical problems. Then you can see if you keep on increasing the features dimensions, then this matrix will become a n cross n, which is a large matrix, and it becomes very difficult for this large matrix to get inverted, because it will not be computationally stable to inverse these matrices when they become very large, because in some of the elements of that matrices may be tend to become 0, because if you do a 1 by 0, it's already it's an infinite. So some of the elements of this matrix may become 0, and because of that, once you invert these matrices, by inverting means you are trying to do some operation like 1 by 0 type of thing. If some of the elements are 0, then what will happen is it will create a situation where you will have infinity and things will blow up. So that kind of situation we try to avoid by using some other technique, so that we should not go with this inversion process, because this inversion process, though it's easy for you to check that it's very easy to do matrix multiplication, do inverse and calculate theta star, but normally this particular thing is very prone to errors. So that's why in order to avoid this type of inversion activity, what we do is we actually go for a gradient descent way of implementing it, which we have already done last time. So this is basically the disadvantage of the normal method. So it's a normal method, the way which is represented over here, it's a normal method. In the starting of the lectures we started out with, right, we will be using two ways of estimating theta. One is normal method, another one is gradient descent. So this is the one method which is normal method. So now what we do is we use gradient descent to do the approach, and the main idea is to avoid this type of problem which is over here. So if I want to do gradient descent, it's nothing but you will be using the derivative of the loss with respect to theta, which is this one, because this is the one which you require, right, to do the gradient descent on the theta. So once we have this expression with us, we can actually take take x dot transpose outside. So once you take that transpose outside, you will get this answer. So this is the expression which is same as the one which you have in the top. And then what you can do is you can use this as the update equation for your gradient descent, because you know gradient descent is nothing but the new value as old value minus the derivative of the loss with respect to old value. So this is the same thing, but now this is the derivative which we are taking over here. And note that all these parameters are now matrix representations. All these theta parameters are matrix representations, and they will be updated simultaneously. And it's not that I will be updating theta 0 first, then theta 1, then theta 2, then theta 3, not like that. Right now this is a complete matrix implementation. So all the elements of this matrix will actually update automatically and in a very faster way as compared to the earlier case, because you can see here there is no sigma involved. So if there is no sigma involved, means it is faster compared to the equation B which we were discussing last time. So here we were discussing equation B, right? So this is the one which we were discussing. So the complete implementation of this in the matrix format is this, which is given over here. So this is the equation if you represent it in the format of a matrix. So any questions here related to this? Okay, so now we will discuss linear regression with multiple features. Right now in the last lecture, what we discussed was a linear regression with single feature where we had only x1. But now we have 4 features here in this particular example, which is x1, x2, x3 and x4. And this is our label, or you can say our estimated value, which is y, which is given in this tabular format. And here you have 4 features, 1, 2, 3 and 4. So all these 4 features along with the y value is given in this table. So here you can see the number of features n is 4, and the total number of samples which we are denoting by m is 24. And here you can see the total number of samples. If you count down in this Excel sheet, it is basically 24 samples. So if I want to pinpoint specifically, what is this sample? This sample is nothing but it's a x1 features first. First sample of first samples feature 1. So this is x11, which the value is 2070. And this is what? This is basically the second feature of second sample, which is 11. So this 11 comes out because of that. So can anyone tell me what will be the answer for x35? Can anyone tell? Sorry? What will be the answer? 1357. Okay. Anyone else? Can you tell what is x3? Huh?
2.5.
Okay. Look closely what I am trying to ask here. I am trying to ask feature fifth of third sample. What will that be? For third sample, I want to know the feature fifth. Is there any feature fifth feature here?
Sir, there is no feature. No.
Sir, there is no fifth.
So it's 0 here. Because there is no features. Okay. What about this x34? What will be the answer for this?
5.2.
5.3.
It will be 5.3. Okay. So now see here. Now we have a matrix x24. That means it's a one-dimensional vector containing all the features. This is all the features which are listed down in a one-dimensional format, and we are taking 24th sample with this one-dimensional feature vector, which is 2016, 1, 1.75 and 6.1. So I am taking this particular column a particular row and making a one-dimensional vector like this x24 with this. And this is analogous to the last case which I was discussing last time. If you see here, in this case, if you recall, this is xi, because it was having only single feature here. So as I told you last time, it will have a single element, but now we have multiple features, so this xi will become a vector now. So this is basically a vector here, like this. It's a vector because you have multiple features, and the dimension of this is right now 4 cross 1. But if you have n features, then this dimension will become n cross 1. As simple as that. So now if I want to do linear regression with multiple features, what it tries to say is that you are actually trying to implement this type of equation. In this type of equation, what you are doing is, now you have multiple parameters along with the features. So if in earlier case we only had these terms were not there. So we only had theta 0 plus theta 1 xi1. But now we have other features also. So we will have theta 2 also, theta 3 also, theta n also. So depending upon how many features you are using, the corresponding parameters of the model will also change, and it will become theta 0, theta 1, theta 2, theta 3 till theta n. So here you can see we are cascading them into a, we are actually we are representing it in the form of a vector which is given over here. So this is a theta matrix, and the dimension of this theta matrix is nothing but it's a n plus 1 comma n plus 1 cross 1. Why this plus 1 coming? Because here you have theta 0 with no feature attached. So basically n features are up to here. This is for these features which are up to n, and then this is the extra feature which is incorporating the incursion of 1. So basically theta 0 times 1. So theta 0 is this one. So that's why it's n plus 1 cross 1. Similarly, your xi is now this. If you recall, earlier case your xi was only xi1, a single element. But now it's a vector which has all the n features, and the dimension of this is n cross 1. And if you want to multiply these two matrices, it will not be possible because this is n plus 1 and this is n. So what we want to do is we have to actually increase the dimension of this matrix by by 1, so that we can actually multiply these two matrices properly. So to do that, to increase the value of this n, what we do is we actually first of all what we will do is we'll create a matrix, bold matrix X, which is given over here, which is nothing but the transpose of the individual samples, training samples. And you recall we had already done this earlier, and now these vectors will not have individual elements, but it's a complete vector here, because you have this vector, right? Earlier it was only a single element, but now it's a complete vector. So once you do the transpose of that, you will get this. Similarly for this up till m, you will get this matrix, which is we are calling as design matrix, and it is also bold X. And note that the dimension of this matrix is m cross n. What it means is, in this dimension here, this is basically the training samples, and here you have features which are up to n, and these are the training samples which are up to m. That's why the dimension of this matrix is m cross n. So this is the design matrix which we are defining by bold X. And now you recall, in order to multiply this theta with this x, I was telling that this is n and this is n plus 1. So what we try to do is we will try to include plus 1 here, so that we can have a matrix multiplication of x and theta. So to do that, we are using x dot. So if you add x dot with 1 in the first column, then the dimension of this matrix increases to n plus 1. And now you can do the multiplication of this x dot with this theta matrix, which is given over here. So once you do that, everything is same as it was in the earlier case. If you recall, the loss function will remain the same, but now the dimensions of the matrix will change. So if you recall, in the earlier case it was m cross 1 here, so it was 1 here, but now it is n plus 1. Similarly, in the earlier case, it was 2 here, because 1 plus 1, so it's 2 here. So earlier in the earlier case it was m cross 2, and the theta was 2 cross 1, but now as the features are increased, you can see it's generalized to n plus 1. Similarly for this, but the important part is, once you do the cross multiplication of these terms, the individual complete matrix, this matrix dimension is 1 cross m, and this complete matrix dimension is m cross 1. And once you multiply these two terms together, you will get a 1 cross 1 scalar value, which is the loss function. And here m is the training samples, so you are dividing it by m. So this is again the vector implementation of that same thing, but for multiple features. Earlier case was for single feature, this is for multiple feature. The loss function is same, the only difference is now 2 is replaced by n plus 1, where n is the total number of features. So now if you want to actually write this for multiple features, the gradient descent equation for multiple features, if you do it without the matrix version, it's like this. Same thing which we had done for the single feature, but the only difference is now I am representing j here as the subscript, and j will be running from 1 to n, where is the total number of features. So in theta j, if I write this as theta 1, if I write it as, it should not run from 1 to n, it should run from 0 to n. So basically we represented theta 0 also, right? So theta 0 will be nothing but theta 0 minus alpha by m, summation all these values. Then we had xi j0. So xi j0 was what? Xi j0 was 1, because we had this one, right? So this one was this. And if you recall theta 1, it will be theta 1 is theta 1 minus alpha by m. So all these expressions, then you had xi 1 here. So I am representing it in a general representation format, which is given over here. So this is non-vectorized implementation. Please note, it's a non-vectorized representation, but now it's for a general feature j, where j is running from 0 to n. So now if I want to represent the vectorized implementation of the multiple feature case, it will be also same as we had done for the single feature case. You can see same thing will happen now, but remember in the earlier case when we were using single feature, at that time x transpose x was having a dimension of 2 cross 2, if you remember. But now if you have n features, the dimension of this matrix is n plus 1 cross n plus 1. And we can see that this particular inversion of the matrix will slow down if n becomes large, and the complexity of this matrix is basically on cube. So on cube is nothing but it tells you how fast or slow this particular inversion will be. So it is slow with the factor of n cube. So as the feature increases, that is your n increases, it will take n cube time to slow. It will be slow by that n cube value. Okay. So normal update, we know we had a problem because of this inversion problem. So we avoided it by using gradient descent, and this is the equation that we have for gradient descent. So in this, basically, if you recall, this equation is also the same as that of the one dimensional feature vector equation, but the only difference now, again I am telling you again and again, is this n plus 1, n plus 1, n plus 1. Earlier it was 2 cross 2, earlier this n plus 1 was replaced by 2. Okay, so now once you cross multiply all these terms, the dimension of this theta will be 2 cross 1, because it's a vector implementation with all these elements. All these elements which are there are the vectors, one dimensional vectors, and these are all matrices. This x star, this x dots are all matrices. So this is my introduction to for the linear regression with both the cases, single feature as well as multiple feature. So in summary, for both these cases where we used single feature and multiple feature, we were using two main approaches for optimizing the theta values, theta 0 and theta 1, or maybe as the feature increases it will be theta 0, theta 1, theta 2 till theta n. We were using gradient descent and normal equations. So I am contrasting here what are the differences between the two. In the gradient descent, basically you require value of alpha, and I told you in details how this alpha behaves if you try to make it too large or too small. So basically this alpha plays a very important role there, whereas in case of normal equation there is no alpha required. That is one of the advantages of using normal equation. The second one is, in gradient descent you need iterations. You keep on iterating for some values till your theta 0, theta 1 till theta n settles down to a specific value, whereas in normal equations there is no iteration required. So it's again an advantage for the normal equations. So in these 2 points, normal equation is actually winning the case. But as your feature increases, the gradient descent actually works much faster compared to the normal equation. So that's why people move to gradient descent, even if they have these two drawbacks. Then also they move to gradient descent, because in this case, as I have told you earlier, because of the inversion, normal equations tends to become too slow. So we use gradient descent to do it. So normally you will not find anyone using this, but they will be always using gradient descent and other optimization techniques to go for for this machine learning thing. So any questions here till now? Okay, so what is the main drawback of this cost function? So we discussed this cost function, right? So it also has a drawback. So let us discuss this drawback and see what we can do to avoid this drawback. This is the cost function which we started out with, and we said that we will be using this cost function because it's a convex function and it has one global minima. So all these attractive properties this cost function has, but still it has a drawback. So let us see what that drawback is. So what happens is, if you recall, this particular cost function is trying to minimize the error between the estimation that the model is estimating, and the actual value of that model, which is yi. So yi is the actual label, and m theta xi is the estimation which the model is predicting out. So what it tries to do is tries to minimize this error. So if the error is large, it tries to minimize that error. Okay, that is the main objective of this loss function. When you take the derivative of the loss with respect to theta and you try to do a gradient descent, so what you try to do is you try to minimize this error. So I hope you know this thing. This is the main objective of finding out this loss function, right? So now in this case what happens is, suppose you have this normal data distribution which is given over here, and you did a L2 regression on this. This is basically the L2 loss. This is nothing but it's an L2 loss. So once you do the loss function for L2 and you perform that gradient descent, and and then once you did the machine learning task and you got these optimal values of theta 0 and theta 1 for this particular case. But suppose now, because of noise, or maybe somebody has deliberately kept a outlier here. So this is an outlier. So what they have done is they have deliberately kept this sample, or maybe because of mistake this sample is here, and this sample is different from the most of the samples which are here. So what happens now in this particular situation, when most of the samples are here but only few samples or one sample is very far from here, what will happen is this line which is given over here, which is the best fit line, because of the presence of this sample, what will happen is this line will shift to this side like this. It will become like this. It will become, just a minute, it will become like this. So what happens now, because of this outlier, this line changes to this line, and you know that this line is not a good fit to this distribution because most of the distributions are here, and your new line is becoming like this, and it's not a good distribution. And why it is happening? It is happening because if you see this loss function, what happens is it tries to reduce the loss, right? So here if you see, for this particular case, the loss is this one. Let us say it's x, not x. Let us say the loss is this loss is, let us say, beta. So if this is the loss, you can see now that this loss is very high and all these losses are very small for this blue line. Okay, but now what is the objective of the loss function? The objective of the loss function is, what is the objective of the machine learning task? The objective of the machine learning task is to reduce the loss. So here this is the very high loss. So machine learning, what it will try to do is it will try to make this loss small. So this loss is actually dominating compared to all these losses. So what is the dominating factor? This is the dominating factor. So what will happen is this line will give priority to this sample, and it will try to reduce the loss for this sample. So once it tries to reduce the loss, the new line will become like this, which is shown over here, and you can see now the new loss is now this. So this is, let us say, beta dash. So you can see clearly that beta dash is less than beta. So the loss is actually reduced when we used when we used outlier. And because of this reduction in the loss, because L2 is giving priority to the outliers, L2 is giving more priority to the outliers, what happens is the equation of the line is shifted, and the shifting of the line, once it becomes red one, it's not an optimal fit to the data set which is over here. So this is the drawback of using this loss function, that this is basically it's not, it overfits to the outlier. What it means by saying overfits to the outlier means it is giving priority to the outlier and it is going close to it to reduce the error. So that is the problem with the L2 loss. So in order to reduce this, what we do is we do not square it. Earlier we were using a square here, right? So now we are not squaring it, and we are actually taking the absolute value. If we are not squaring, so what we do is we just do a absolute value of the difference between the model from the prediction of the model times the actual label. So once we do this, it is basically also called as least absolute deviation cost, and the new loss function is this one. So this is the new loss function where there is no square, and because there is no square, we do a absolute sum so that the errors should be summed up rather than addition subtraction happens. So we try to sum up the errors rather than basically if you do a minus b, we do not want to do that. We want to do mod of a plus mod of b, so that we can get the actual value of the loss. We do not want this reduction to happen. And by using this particular thing, what we are trying to do is we are trying to actually treat all the negative and the positive errors equally. So we try to do that, and what will happen now is it will stop giving importance to the large errors, because you are not squaring, right? So if you are not squaring, so even though if error is large, it will not be given that same importance. It will be given less importance compared to the errors which are made by this one. So if you compare these two cost functions, so this is basically the one line fit. This is the line fit with this loss function. So this line fit, you can see if I am using the modified loss function, which is m theta xi minus yi absolute sum. If I am using this loss function, I am getting this equation. If I am using L2 loss function, I am getting this function. And I told you already that this function is how it is, affected by this outlier. But the modified loss function is not affected by this outlier too much. It will be affected, but it will not be affected too much. This one is affected more compared to this one. And you can also see the plots, the gradient descent plots here, and you can see that the least square, which is also called as the L2 loss, how much error it is making. This is basically the loss. So you can see how much loss it is making as you go from k equal to 0 to 100. And you can see the purple line, how much loss it is making when it is moving from k is equal to 0 to 200. So by modifying the loss function, you can actually do this type of thing. Okay. So now there is another concept which we call as weighted regression. So all these regressions are the ones which we have discussed are normal regressions, but we have some variations in the regressions. So we are discussing that variations now. So the first variation that we will discuss is the weighted regression. So in this weighted regression, what we have some duplicate values also. So if you see here, we have some plotting of the data for a particular experiment. So in this experiment, what happens is when the person is performing the experiment, there are some values which it is getting. So let us say it is getting, 2 point, for this particular case, let us say it is getting 0.256. Another value it gets is 0.257. Another value it gets is 0.253. And something like that. So it will get multiple such values. So what happens now is, if it gets multiple such values, and so normally what they do is they sometimes they try to truncate it also. So if I try to truncate it to two places, then this value will be 0.25, this value will be 0.25, this value also will be 0.25. So the important thing that to note here is, when we do some practical examples, it happens that some values become duplicate. So here you can see, even if we have 3 different samples, for each of these 3 different samples, the value, if you truncate these samples, it will become same. So it's a duplicacy that is coming into it. So we have now 3 samples which are of having same value, which is 0.25. So what it tries to show here is, if you see the volume of if you see the area of this dot, the bigger the area of the dot means more number of samples are here with the same value. The smaller number of dot means smaller number of samples with the same value. So for example, if it is this dot, that means it has a value of, let us say, 2.5, 20 such values are there. And if it is this value, then it means it has a value of 2.5 and only, no, not 2.5, it will be some value, let us say 1.2, and only 10 values are there. So like that, we are plotting these values over here. So you can see we have these data points with variation in the size of the dots. The bigger the dot is, the more more samples, similar samples are there in that. So if this is the dot, if you are looking at, this dot will have more number of samples compared to this dot or this dot. So if you have this type of problem setting, how to tackle these type of settings. So you want to do a linear regression here, right? So how will you do linear regression on these type of data sets where you have duplicacy in the data like this? So it's not too difficult to see that if you have duplicacy in the data, there is no problem. What you have to do is you have to just expand this term first. So you know this term is expanding from 1 to m. So this term is going from 1 to m, which is the total number of samples. So if you expand these terms from 1 to m, so whatever terms which are having common value can be clubbed together into a single term. So here, if I say, let us say x1 sample is coming beta 1 times. So what I will do is I will club all these terms together, and this is the beta 1 times x1 sample is happening. Plus, if x2 sample is happening beta 2 times, then we will club all these samples into one term, and we are calling it as beta 2. So basically these two total terms which we are clubbing together are beta 2. Similarly, the mth sample, if it is happening beta m times, then we will club all these samples with the same value in single term like this, and they are total beta m terms. This is beta 2 terms and these are beta 1 terms. So this is nothing but just expansion of this summation, and it's very easy, right? So what you are trying to do is you are trying to sum up the similar terms together, clubbing up the similar terms together, and finally you are doing the summation, because summation is the main thing which is going on here. So once you do this in the compact fashion, in the compact representation, you can represent this complete expression as this expression. This is also very simple, right? All these expressions, for individual xi's and yi's, you have a corresponding beta i's associated with that. So if I go for sample, let us say fifth sample, the model estimates something correspondingly the fifth, and if you have 20 such samples, and then 20 will come on the front side, and if you have 10 samples of x14, then basically it is nothing but like this. So if you keep on expanding all these terms, what you will get finally is the same summation which is given over here. So this is basically the expansion, but you are keeping the beta i's for the corresponding repetitions of the samples xi. Basically this is actually incorporating the how many samples are same. So this thing can be represented in the matrix representation like this, with beta I over here, and here you can see this is the total samples here, because at the bottom we had m. So m is nothing but how many times your beta 1 is repeated, beta 2 is repeated, beta m is repeated. So all this sums up to m. So here you have the complete expression for the loss function for samples which are having duplicacy in the values. And then what you can do is you can take the derivative of the derivative of the loss with respect to theta for this modified loss function, and you can get the answers. And then you can use gradient descent to go for doing the updates. So here I am showing you a graph which is actually basically trying to tell you that same story. So what it is trying to show you is that this is the normal fit to the data. Here all the data points are having similar size, but what happens now is, as this size of the dot increases to this, you can see how this line is shifting towards this dot. So you can see as the size increases, how the line is shifted towards the bigger dot. And what it tries to show you is that if the size is increasing, means the weightage corresponding to this dot is given more. That is the thing. Here the weight is less, here the weightage given to it is more, here the weightage given to it is more than this, and here the weightage given to this is more than this. So as the weightage is given more and more, which is represented in the format of the size of the circle, you can see the line is shifting towards these dots. So this is basically trying to show you that if the samples have, if more number of samples are accumulated on these dots, then what will happen is, the line will give priority to these samples, and all these lines are L2 lines. and if you use the modified loss function which I have discussed earlier, then it might be the case that the line will not shift that much. It will shift, but it will not shift that much if you use this particular loss function which we were discussing here. Okay, so this finishes off with the lecture here for today's class, and group 1 will prepare lecture notes till this point, and they will submit me this particular thing by end of the next week. So I'll give them again one more week to do it. So if they are here, they can do it. Otherwise, I will post it on the classroom also. And then any questions here? Okay, then thank you so much for attending the class. You have any questions? Okay, thank you so much for attending the class. Okay, bye.